The discovery and properties of the electron. The discovery of the electron begins with a scientist by the name of Thomson, and he was able to measure the ratio of the electric charge of an electron to the mass of an electron. And at the beginning of his experimentation, he did not know that he was dealing with electrons, but so they were called cathode rays. There were many scientists that were trying to figure out what they were. Some scientists believed the cathode rays were beams of light, and some people believed that no, they must have some sort of mass or charge because they interact with electric fields and magnetic fields. So with this discovery of cathode rays, experimentations were done with these to try and figure out what they really were. And so there was a big experiment done by Thomson where the cathode rays are accelerated by a high voltage, and then they travel between a pair of parallel plates with an established uniform electric field. Imagine we have an electron being accelerated to the right, or aka a cathode ray, and that cathode ray moves through two parallel plates, and the parallel plates have a voltage difference between them, so there is an established electric field. As the electron moves through the plates, there is an electric force from the electric field that allows the electron to deflect in a direction like so. This can also be done with a magnetic field. So imagine I have coils of wire with a current going through it, and I have my cathode ray moving through this magnetic field, and we get a deflection going this way. Based on this curvature, this deflection, what scientists did is they said, oh, there is a magnetic force acting on this cathode ray, and that cathode ray is moving in a circle, so this magnetic force is also the centripetal force. We know magnetic force is QVB, or in this case, because we're dealing with an electron, it's an EVB. And we know centripetal force is mv squared over r. Simplifying this equation, we can see that we have a ratio of the charge on the electron over the mass, and that is equal to the speed, the tangential speed, divided by the field, and divided by the radius of curvature. After this discovery was made, cathode rays were soon to be called electrons. There was still one little issue here, and that was the scientists did not know the value of the speed of the electron. The magnetic field could be measured, the radius of curvature could be measured, but the speed could not. So there was another setup where the electron is sent through a pair of plates that have an established electric field through them, and there's the magnetic field established with a coil of wire around that. And because there is an electric field and a magnetic field, these can be fine-tuned so that when the electron moves through, it's undeflected. And so we have this undeflected V. And this is all based on Newton's second law of motion, where the sum of the forces acting on the electron as it moves through the electric field and the magnetic field, that the forces on this electron cancel. There's no acceleration. So we use Newton's second law of motion, which says the sum of the forces is equal to ma. There's an electric force upward. There is a magnetic force downward. And the electron is moving at a constant speed undeflected, so this is equal to 0. Therefore, the electric field and the magnetic field are equal, or we can say the electric field multiplied by the charge on an electron is equal to the charge on an electron multiplied by its undeflected velocity multiplied by magnetic field. And by rearranging this formula for V, we can see that the speed of this electron is equal to E over B. Now what scientists did is they went ahead and plugged in this equation for V and put it in the above equation here. And by doing that, we get a final equation for E over M. And E over M is equal to E over B squared over R. Now the next part of the discovery of the properties of the electron was established with a very, very famous experiment called the oil drop experiment by Robert A. Millikan. Not only does this experiment find the charge of an electron, the actual value for E, but then from our previous discovery by Thomson, we could also figure out the mass of an electron. And it was through these discoveries it was shown that charge comes in discrete amounts or packets, which we will be talking about a lot more later on. Now, in this experiment, tiny droplets of negatively charged mineral oil were allowed to fall under gravity between two parallel plates with a uniform electric field. So we have these two parallel plates with the uniform electric field established. And then there were these negatively charged oil droplets that were put in between these plates, and then they were under the influence of gravity, so they should fall downward. But because there's an electric field between the plates, there was actually a force of gravity pulling downward on the charge, and there was an electric force pulling upwards. So we have forces that are in opposite direction. By modifying the electric force and therefore the electric field, we could apply Newton's second law of motion again and see how, of course, the sum of the forces is equal to ma. In this case, it's the electric force minus the weight or the gravitational force. If the oil droplet is suspended between the plates, we say that's equal to 0, or the electric force is equal to the gravitational force. Now, electric force is electric field times the charge on an electron in this case, multiplied by the mass of the electron multiplied by the acceleration due to gravity. Or the charge on an electron is equal to the mass multiplied by g over E. And this was determined to be a value of 1.6 times 10 to the minus 19 coulombs. I have one correction here. This mass is not the mass of an electron. This is the mass of the oil droplet. And that's really important because at this time they didn't know the mass of an electron. So this was the mass of the oil droplet. Now once the charge on an electron was discovered, and we already knew the ratio of the charge of an electron to its mass, then the mass of the electron could then be calculated and came to be 9.11 times 10 to the negative 31 kilograms. And this is the mass of an electron. As you can see, this mass is so small, so much less than the mass of one particular atom. And so what scientists were also saying, especially Thomson, is that the electron must be just a part of an atom, a subatomic particle of the atom. All right, here's your practice of numbers 1 and 3. Good luck.